So pH curves and indicators is the theme. We need to know the shape of the pH curve, but the real point of this lesson is to be able to pick what indicator is going to work. We need something that changes color that tells us to stop, and we can't always use the same chemicals. So in this example, we're going to have hydrochloric acid is titrated with sodium hydroxide. Now the sequence of this wording is really important. It tells you a lot. Okay. The word with splits the sample which has to come first. And this will apply in chemistry 20, also in chemistry 30. Okay. You have hydrochloric acid as your sample. It's titrated with, or you're adding the titrant. So we're going to start acidic. We're going to measure the pH of the Erlenmeyer flask, which would have the sample, and we're going to add sodium hydroxide, a base, to it. What we're getting started with is a strong acid titrated with a strong base. Okay. So we have something from the very top of our acid-base table, which is strong, with hydroxide at the very bottom. Sodium is a spectator ion. It isn't going to do anything. So I have the balanced double replacement type acid-base reaction. The H and the OH make our water. If you end up with a diprotic species, you end up making two waters. And the sodium and the chloride, a +1 and a -1, we get our salt. So pH curves always have these axes. The volume of titrant is on the x-axis. So I'll be a little bit more thorough. Often we're sketching these and not putting in the exact numbers. If you're just doing a sketch, you'd be fine to leave out the volume. The y-axis, or the responding axis, is going to be pH. That will respond or change depending on how much titrant we add in. So I'm going to get started at 0 volume. We have an acid sample, so we're going to start somewhere low. We don't know exactly where. If I told you the concentration was 0.1 moles per liter, you could take the negative log of it. Because it's strong, it would 100% turn into hydronium, and the pH would be 1 if I gave you the concentration like I just added in. Okay? But you know it has to start low. As you add hydroxide in, as the volume of titrant goes up, okay, all of the base that we add is going to get consumed by the acid. So there's not going to be any hydroxide in our solution, or any of the added. So you're going to see the pH be almost flat. I have a very slightly increasing slope. It's drifting upwards, but we have a big pool of acid. We're putting a little bit of base into it. It reacts away. And that's what happens through most of the addition of the base up until the point where we start to run out of the acid. When we get close to running out of the acid, the pH is going to shoot right up. So it's not a subtle drifting up. Near the end, it's a massive shooting up. And the point where you've run out of acid, you've no more hydrochloric acid, will occur at a pH of 7 with 2 strong species. And we call this the equivalence point. This is a 1-to-1 acid-base ratio. So this is the point where there's equal moles of each reactant. We don't call it equal point because not all reactions are 1-to-1. So if this was a 2-to-1, maybe a diprotic acid and a monoprotic base, okay, an acid that can release 2 H's, a base that takes in 1, you'd have a 2-to-1 ratio, and the equivalence point would be exactly when you have a 2-to-1 molar ratio between the chemicals. After that dot, the equivalence point at 7, we're still dumping in base, so the pH is going to keep shooting up, and it's going to level off, and this will level off at the pH of the base. So if the base has a pH of 13, it'll level off at 13. There's nothing to do with the chemistry per se. There's no chemistry going on after that dot. You've run out of HCl, you're just dumping in acid. Okay. The goal in a titration is to stop when we get to that equivalence point. So we can do our ice table, we can do our stoic. Okay. We know that both chemicals have run out. This you may not want to add into your notes. Okay, well, we get ICE. When we're at this equivalence point, there is no moles of either of the reactants left. And that should look familiar, putting zeros in when you're comparing one reactant to another. So that's a pH curve. We've got that theoretical equivalence point, but we need something to tell us when to stop. We're going to need an indicator. We're going to talk a little bit about indicators now. We're going to talk about that phenolphthalein, and then I'm going to add the colors in to that graph. So for a titration like this, the most common indicator is phenolphthalein. The short form in your booklet is HPH for the acidic version and pH minus for the basic version. So I'm going to be grabbing information from page 10, phenolphthalein for this example. So this is where I got the HPH shortcut. You're going to see these numbers, 8.2 to 10, show up, and that colorless to pink color. So I like to summarize all that data in your booklet in a number line that I've split into 3 pieces. The low pH was 8.2, thank you. The top is 10, and we have clear. We have pink. It's a quite dark pink, even with 2 drops of indicator in a titration. It is intense. But in the middle, we get a light pink or a faint pink. Now, in this particular example, we are starting with a low pH. So we're going to be going through these numbers from low heading to high. So when we use phenolphthalein, HPH, the first color change we're going to see is clear turning to light pink at 8.2. We use the first color change in indicators, the first color listed in the book to the combination color. The clear and the light pink, the clear and the pink makes light pink. I'm going to label that, and then finally I'll actually get to the reaction of what's happening with our indicator. So in our titration, we're clear. Now, I don't have a clear color, so I'm going to use black for my clear. So when the pH is 1, we're going to be clear. The pH is going to shoot up. It's going to be clear. It's going to go right through the equivalence point. We're not going to see it. But at 8.2, we're going to start to see a light pink. Now, I'm just going to use my red pen for light pink. And that's when we're going to stop at 8.2. Now the pH is shooting up so steeply, the volume at 7, our black dot, and our volume at 8.2 are the same volume. It's going up so much, the fact we're 1 pH unit high will not change our result. As long as we don't start dumping in 5 mils of indicator, you go crazy and you put in 10 drops of indicator and now you're adding so much chemical, you're starting to alter things. But 2 drops does not cause any error. Now, this point where I have my black line, which is meant to be clear, turning to red, we call an end point. So equivalence point is theoretical. It's where we want to stop. It's where we have that molar, equal molar ratio for this particular example. We can't see it. So we have an end point, which will be clear to light pink. And this is going to occur at 8.2. At 10 is where things will go super dark. And you know you've blown way past the 8. Now, when you do a titration, particularly your first one, you're going to see that dark pink a bit. You'll find that 2 extra drops of titrant, and it's going to go past light pink and be really dark. And that's the type of thing you want to record in your book, both how dark it went and how many drops you think you might have added extra, because that gives you some information about the quality of that titration and whether you want to keep or exclude that one. So last, what exactly is going on with that indicator? So we've got 2 forms written in your data booklet. We've got HPH, which is the acidic form, and this is clear. It has no color. So the first acidic piece written in your booklet goes with the first color. I'll just flip to your table for a second. So HPH, with the H, that's the acidic piece, goes with pHs below the first number and goes with the first color. When the H is removed, that happens above the second species, happens above the second number and is connected to the second color. Okay. Indicators are just acid-base combinations that happen to have colors in one or both. So in this example, we have HPH. You would have put that indicator into solution. You're going to titrate in acid. Sorry, base. You're going to titrate in hydroxide ions. And when you've titrated in enough hydroxide that they stay, you'll cause that H to come off and transfer to the base. And you'll get water. And this species is pink. But you need some of the hydroxide to stay. You need to get a little bit past the equivalence point where hydroxide is building up to flip from the clear species into the pink species. And you want to stop when the eye can pick up any amount of that species, because that tells you there's hydroxide starting to build up. Again, this is super picky. In high school, you're trying to get within a drop or 2. In post-secondary, you'll be adding maybe half drops or quarter drops to increase your precision. In high school, you're evaluated on developing the skills, okay? Knowing how it works. In post-secondary, you'll actually be evaluated on how good is your number, how careful are you, how close are you to the correct answer. So that wraps up our first slide, which pretty much all the theory of this lesson was presented on. We've got this shape you should be familiar with. It's flattish, massive shooting up, leveling off. Volume of titrant is our x-axis, pH is the y, and we talked about equivalence point and end point. You're going to see those 2 on tests, and you have to keep them separate. They have very different meanings. Ideally, they're in the same place. but one is theoretical, one is based on visual observations. So a second example. Calcium hydroxide is titrated with hydrochloric acid. I'm going to draw the pH curve and label both the equivalence point and the end point. Now, calcium hydroxide is not very soluble. If you looked it up in the table, you'd say it's solid, but a little bit of it is soluble. Okay. But you couldn't have a very high concentration. We've got that titrated with, which separates our sample and our titrant. It's kind of the first thing you want to look at and decode the sentence that has the titrated with. It is always the sample first and the titrant second. So I flipped where the acid and base are in this example. We're starting with a base this time and we're adding an acid. They're both strong species. The calcium hydroxide will just dissociate 100% as long as we only put a little bit in. The acid will ionize 100%. What's different with this one is we're now with a base sample. So we're starting high instead of starting low. I'm not going to put a concentration in so we don't know what pH it is. It wouldn't be super high because of the low solubility. We're going to see the mirror image of the previous slide, top to bottom. We're going to slowly drift down as the base chews up, reacts any acid we add in. Eventually, you're going to run out of hydroxide and it's going to drop down. You're going to hit the equivalence point. Where you have an equivalent amount of each moles according to the balanced chemical equation. And then you just keep dumping in acid and it's going to drop like a rock and level off at the pH of the acid. And it should be perfectly flat at the end. We're going to need to pick an indicator somewhere around 7 that's going to change color for us. Now, phenolphthalein isn't going to work. For one, pink going clear is not easy for the human eye to pick out. So it's not a great color change. And then also what doesn't work is where the pH is. If you use phenolphthalein like we did before, we're no longer going in this direction at 8. We're coming at it from a high pH dropping. So you'd be starting to see a dark pink to light pink at 10. Now the human eye is really going to struggle picking that out, that first color change. So we want to pick something else. I'm going to lay out our number line that I'm going to break into 2 pieces. And I'm going to remind myself that we're starting at a high pH and we're dropping down. So I'm going to put an arrow in that represents high pH dropping down. We're going this way through our numbers. So what is close to 7, within a unit or a unit and a half is fine, but it's the second number. And the most commonly one used for a sample titrated with a base is bromothymol blue. Okay. The second number is 7.6. So just slightly 0.6 pH units above 7 or the equivalence point. So I'm going to pull these numbers into my number line. So we have 6.0 to 7.6. The colors are yellow below 6. When it gets really acidic, it'll be yellow. When it's above 7.6, it's going to be blue. And when we're in the middle, yellow and blue make green. So our first color change, we're going to see blue turn into green at 7.6. Okay. So most high school and first year or second year university labs, these are the two indicators you'll use a lot with strong species. Phenolphthalein for the first slide, when you have an acid with a base. When you have a strong base with a strong acid, you'll use bromothymol blue. Now I can label those colors. We're blue at the high pHs. So we're going to be blue. The pH is going to drop and it's going to stay blue until we get to 7.6. At 7.6, we're going to switch to green. And it's not going to be green very long. It's like one drop or half a drop, it'll stay green. Because it's dropping down so much, you'll quickly get into the yellow at 7.6. But your goal, your end point is at 7.6 with that blue to green color switch. So in a second, I'm going to draw this pH curve. This is beyond Chem 20, but picking an indicator based on the sketch is fair game. So as I draw the sketch, you may want to be looking at page 10 of your data booklet, seeing where I put the equivalence point, and starting to think of what might you pick. Now, instead of giving you a sentence with the word with, I've just given the equation and I labeled the sample and the titrant. There is no convention in an equation that the sample has to come first or second. So if you're given an equation, look at the wording to figure out which is which. Okay? But we're going to start with sodium carbonate as our sample, weak, polyprotic. Okay? We're going to titrate a strong acid. So let's see what that pH curve looks like. So we are starting with a base sample, so that's not new. I would fully expect you to start up high. Okay. But because it's polyprotic, we're going to see two drops. We're going to see one drop and a level out, or we're going to see a second drop and level out. Now, all this theory will come in Chem 30. All the equations will come next year. We're going to end up seeing two equivalence points. And when one of the species is weak with a strong species, the equivalence point isn't going to be at 7 anymore. And in Chem 30, you'll learn how to predict where it shifts. But this is what you'd get when you have a diprotic species with a strong species. And we're going to think about what indicator could we use to study this second equivalence point. So this is equivalence point number 2. It's when all of the carbonate has picked up its second H, perfect 2-to-1 ratio, and we maybe want to stop our titration there. So I have to think, what indicator would we want to use? I always think of indicators with number lines. We're going to have to think of which indicator, pull the two numbers, and we're starting high and dropping down. So the high numbers are on the right, and we'll be heading towards the middle, and ultimately, if we go too far, to the left. So let's see, what would we have well below 7? We're going to have a few options. So we're well below. We are going in this direction in this particular example. And I'm going to pick orange 4 for my endpoint colors or my indicator. You maybe could have used methyl orange. Okay. Thymal blue would also have the same second number. So there's a few options you could have picked. Okay. But you want to pick something within a pH unit of the equivalence point. Second consideration, what can the human eye pick out? Okay. Some color changes are difficult, others are more easy. The easiest is clear to pink with phenolphthalein. But phenolphthalein is absolutely useless to us. It's going to change color at 8 to 10, and that's nowhere near this equivalence point. So we can't use kind of our favorite. Okay. So I'm going to use orange 4. Sorry, HOR, which was 1.4 to 2.8. I don't have a labeled axis, but it looks like it's down around 3-ish where I put that dot. Now, I should have labeled my axis first. In my head, I kind of had 0 as the bottom and 7 as my dotted line. So what are our colors? They're red to yellow, and red and yellow make orange. Triple check, so I'm getting those from there. So if you weren't sure where they came from, the orange isn't written in, but it does happen to be in the name. So what's our endpoint going to be? We're going to be yellow through most of this titration. You're not even going to see a color change for the first equivalence point. And at 2.8, we're going to switch to orange and stop. So my arrows are kind of going to the same place. The end point is yellow to orange at 2.8. And it should do a pretty good job of telling us the equivalence point. And then this would lead to stoic and calculations. Okay? We want to get the volume at the equivalence point, and we'll get it by the volume at the end point.